Le Chatelier's principle is when an established equilibrium is then disturbed by changes in concentration or temperature or volume. In this one page of notes for Unit 7 in AP Chemistry on equilibrium or your college level course, I will only be covering concentration changes. I'll make a separate video for temperature and another one for volume changes. To understand what's happening with the Le Chatelier principle, which is defined here, we are going to have to review the reaction quotient called Q. K is the equilibrium constant, and Q is the reaction quotient. Now, they're very similar in the fact that they're calculated the same way. So you've got your product concentrations over your reactant concentrations, and we'll stick with these being like QCs and not a QP, meaning not pressures. And what happens is if for some reason you put those numbers in there and they equal the K value, in this case, I'm going to have the K value just be 2, it just made up a number. And if that equals 2, then we are at equilibrium. If it does not equal 2, then we are not at equilibrium. So what that means is that Q would either be greater than K, meaning greater than 2, or it could be less than 2 for this specific example here. But if it does not equal 2, then we are not at equilibrium. And what can happen is this Le Chatelier principle. So let's cover the first example, which is what if we increase the concentration of the reactant after equilibrium has been established? So what would that look like on a graph? So I'm going to zoom in here and show you what it looks like to disturb the equilibrium by adding a reactant. So right about here, we've reached equilibrium, okay? So this is kind of the kinetics portion of the graph where we make more product and the Q is less than the K. I talked about that in a previous video. And then here is where we've established our equilibrium. The concentrations are no longer changing. And then we disturb the equilibrium in this case by putting in some reactant, the red one, okay? And then that's going to go back down, but not below the original. And then all of a sudden the product's going to increase. So here's where the Le Chatelier portion happened, probably right between those two sections. And then it reestablishes the equilibrium where the Q and the K are equal. Let me actually put the Q first here. So the Q is going to equal the K again, which means it's going to be equal to 2. But before that, the Q ended up being less than the K. So let's figure out why over here in my description of it. So what happens is when A is increased, the Q becomes less than the K. Take a kind of look here. All I did was sort of say like the denominator is going to get bigger. So then the reaction is going to shift right to make more product so as to receive more product and reduce the reactant and achieve the same K value again. That's important that we're going to establish a new equilibrium position, different concentrations, but it's going to equal the same K value. All right, so that's the first one. So what you'll hear a lot of times in textbook is if you increase the reactant, it's going to shift right, it's going to make more product, but it does that in a way to reestablish an equilibrium that has the same value of 2 in this case, okay? All right, next. What about if we decrease the reactant? It's going to kind of get rid of that. So we have our new Q value here is actually going to be greater than K. And that happens because the concentration of the reactant goes down. So on the graph, it'll look like this. It'll reestablish equilibrium by using up some of the product and create more reactant, but not more than it had before. Just put some more, back in. So let's go over like a little bit why that happens. So if you look back here again, we've got Q less than K. Make more product. We establish an equilibrium. So Q equals K. And then we disturb the equilibrium. And then we reestablish it again, but this is where Q is greater than K. And then Q is going to go back to equaling K again with some new concentrations with the same K value. And so what you'll hear a lot of times in textbooks, if we remove A, it's going to shift back to the left. You'll have to use up some product to create the reactant that's missing. But on a graph, it's going to look like that and then like that and give you the same, again, equilibrium constant with new equilibrium values in there for the concentrations. All right, so we have 2 more. Basically cover all the options here. So the next ones are going to be about the product. So I'm just kind of zoom into those 2. So kind of think ahead if you can kind of predict what's going to happen. So if we increase the product here, and then it'll go back down, and then we'll make the reactant. So kind of think about what values are going to happen with the Q and the K. Just going to kind of map off the same sections here. So again, Q is less than K. We reach equilibrium where Q is equal to K. Then all of a sudden we disturb it by changing the concentration. This time we're going to add product. And then we have again reestablished that Q is equal to K again. So if you want to know like what happened to our K value and why, I'm just going to erase this. So there we go. We've got the product increasing. So the Q is going to be greater than the K. So we can add that in here right here. Q is greater than our K. And that makes sense because if you think about it, you're putting a larger value in the numerator. And so we're going to shift to the left to create more reactant and to reach the equilibrium constant again, but again, new equilibrium position, meaning that the concentrations are different. And what I mean by that, again, is like if you put these two concentration numbers, you go back over to the graph over here, okay? And then you try these two new concentration units, like I'll just put like a little X. How about we put an X like here and here, and we go back over to the graph there and like there. What we're saying is that those concentrations, when you put them into this Q value, will then establish the same K value if it's at equilibrium. All right, last but not least, we got one more choice, which is what if we decrease the concentration of the product? That's what the graph would look like. Again, kind of zoom in. We've reached equilibrium here. It's established an equilibrium, then we've disturbed the equilibrium, and then the equilibrium has been reestablished. So I'll just kind of work backwards. Q would equal K, Q would equal K, Q is less than K. And then again, Q would be less than K again here because we're, again, trying to, we take away the product, but we got to put more back. So the reactant is consumed to create the product that was removed in there. And then you can look at kind of the math of it, which is, again, if the numerator goes down, then the K value stays the same, but the Q value becomes less than the K. So we shift right, and we achieve the same equilibrium constant with some new equilibrium concentrations. All right, so that's basically the Chatelier's principle using concentration. Just kind of zoom back out here, let you see all four of those possibilities. And again, I'm going to cover changes in temperature in a separate video and changes in volume in another video, but they're going to have kind of a similar type of feel to this with the Chatelier principle. So I'll just review it one more time. We'll just look at the reaction itself though. So again, if we increase the concentration of A, it's going to shift right. It'll produce more product to reach, again, the same equilibrium constant. If we decrease the reactant, it's going to shift left to try to replace what's missing. If we add product, it's going to shift this way to the reactant side to create more of that to equal out to get the same equilibrium constant. And then last but not least, if we take away the product, it's going to shift right to try to replace that product that is there. All right, so that's the Le Chatelier principle using concentration changes.